Hello, my name's Simon Maskell. I'm from the University of Liverpool, and this is joint work with my PhD student, Alessandro Varsi. We're going to talk about how we are working towards building an interface for a streaming version of Stan. So our fundamental motivation is that we want to replace or provide the capacity to replace the use of ODEs with stochastic differential equations in Stan. So at the moment, if you want to tackle, for example, as we are trying to problems that relate to coronavirus, you've got to assume that the spread of coronavirus is governed by an ordinary differential equation, i.e. a deterministic function over time. And that doesn't actually describe dynamic systems in the much fidelity as we would like. So we would like to replace the use of the ODEs that we're considering with SDEs. We'd also like to be able to process data over time as it comes in. But our fundamental motivation is the ability to consider stochastic differential equations in Stan. So we're going to introduce a bit of notation before we kind of dig into anything. So we're going to assume that theta is a constant parameter that takes a fixed value for all time. We're going to assume that t is a time index. And we're going to assume that y1 colon t is a data set. So 1 colon t means 1, 2, 3, all the way up to t. So that's a data set with t elements. The data set is recorded over time, and we're going to assume that each time epoch there's a corresponding state x which is unobserved. So there's a x1, x2, x3 all the way up to xt, and we call that x1 colon t. So that's our dynamic state sequence. We might, for example, measure the stock price and wish to infer the current volatility of a stock. So in that case, YT would be the current stock price, and XT might be the current volatility of the stock. We might also wish to land a rover on Mars, in which case YT might be the measured altitude from some noisy sensor of the height of our lander vehicle from the Martian surface, and XT is perhaps the true height of the vehicle above the Martian lunar surface, sorry, Martian surface. Land on a moon later, and XT might also include the velocity, the vertical velocity of this lander, which might be pertinent to some control system that meant that the thing wasn't going to smash itself to bits when it landed. In any case, we're going to have some probability distribution that we want to calculate, and we're going to write probability distributions with p and things in brackets. Typically, those will be intractable and awkward to sample from, so we're going to sample from something else called Q, which is a distribution we can sample from analytically. We use important sampling to correct for the disparity between P and Q. And we're also going to consider X subscript T superscript J in brackets to mean the jth particle at the tth time epoch. Just in brackets so that we avoid confusion with being xt to the power j, which has confused people in the past. So Stan's a great tool for Bayesian inference. It focuses on sampling from the distribution of some parameter theta given some data set y1 to capital T, where T, capital T, is fixed. So we give it a big lump of data, we want to figure something out, and we use Stan to do that. That's a form of batch analytics, and you can solve batch analytic problems using MCMC, e.g. the nuts algorithm that's inside Stan and does a good job of generating samples, as we hopefully all know. But wouldn't it be really good if we could use Stan in other contexts? So imagine you have an incoming data stream, as I was describing before, and every time you take 1 day forwards, you get a new stock price, or every time you go 20 milliseconds forwards, you get a new measurement of your Martian lander's altitude from the Martian surface. And we want to know what's the probability distribution of the new value of x at the tth time step, given all the data we've ever seen up to now. And we're going to get more and more and more and more data over time. As time evolves, we're going to change what it is we want to know, and we want to keep on figuring out what we know from all the data we've ever seen. Now that's a form of streaming analytics and can be solved using particle filters, abbreviated PF. So our focus here is on defining the interface for a particle filter variant of STAN. We call that PF STAN. Now, it turns out that in other work, we've figured out how to sample efficiently in particle filters. So we're not really going to focus on that here. What we're focusing on here is how can we describe the models that are pertinent to particle filtering in the STAN syntax, such that when we generate a open source variant of STAN that can handle these kinds of problems, the interface is specified in a way that the users, that's you, would be aware of and would have commented on now, so that we can anticipate any issues that you can spot with what we're planning at this present time. So just to kind of give you at least an inkling as to what will be going on under the hood. So mathematically, though not actually in terms of what the algorithm does in operation, we define a joint distribution, P x1 to t, comma y1 to t. So that's the distribution of all the states you've ever thought of before up to the tth time step, and all the measurements you've ever had up to the tth time step, that's y. So the trick, if you like, is twofold. So one is that you assume the sequence is Markov, and one is that you assume the measurements y, t are independent of everything other than the current state. Given that, we can write the output at time t as the output at time t minus 1 multiplied by the dynamics pxt given xt minus 1. So that's how we think the thing that we're interested in evolves in time, multiplied by a likelihood, pyt given xt, which is how we think the thing we all measure, yt at the tth time step, relates to the thing that we don't know, xt at the tth time step. So what we want to be able to do is to define and later use the incremental joint distribution, so the product of this likelihood and dynamics term. And we also need to kick the thing off into action, so we need an initial prior to kind of initiate the recursion. We can use essentially conventional STAN syntax for these distributions, as I'll go on to show you. And what we output at each time step t is samples and weights that represent p of xt given y1 to t, the thing we want to know about. And we want to be able to use STAN so that we can flexibly define all the distributions we're interested in. And as I say, we have something analogous to NUTS that enables us to sample very efficiently, in the same way as NUTS enables you to sample very efficiently in the batch analytics context. So we employ a particle filter. I won't talk about how it initializes at t equals 1 because that's less exciting. What we do is we sample xt, or the jth sample of xt, by taking the jth sample of xt minus 1 and yt, and then coming up with some distribution q that is a function of, well, the distribution over xt, and we sample from that. We call that the jth sample of xt. We can choose any q we like, kind of. There are restrictions, and you can choose some pretty rubbish ones, and they're well published in the literature. There are some neat ones that we think we've come up with, which enable us to be confident we can sample generically well, and that uses NUTS, as I kind of hinted. We then, since we sample from Q and we're actually interested in P, we can make the new weight that we're interested in, which describes, if you like, it is the importance weight associated with xtj. That weight is wtj. That's actually equal to the old weight of the jth particle, wt minus 1j, multiplied by the ratio of the incremental joint distribution and this proposal. So if inside PF STAN we calculate and draw samples from Q and can calculate Q on the bottom, and we've got a STAN file that describes P on the top, the SMC so the particle filter can calculate the weights recursively and calculate the samples recursively. So if we have that, we get weighted samples xtj, ytj for all j 1 to n, where n is the number of particles or number of samples we have. And then we can estimate quantities of interest as essentially a weighted sum of some function that we're interested in calculating the expectation of for xt superscript j. And we can do that so long as we can resample and choose a good queue, both of which essentially will happen under the hood. So from a user's perspective, you don't need to worry about that. We do, and we have for several years. We'll just make it so that that's something you can use. So let's make a specific example to try and bring this to life a bit. So imagine that we had an object moving in 2 dimensions, for example, my telephone. And then the telephone is moving, and it's moving in a 2D plane, and it's moving such that it has some position and velocity in x and some position and velocity in y. And we assume that the x position we'll call x comma t at time t. The x velocity we'll call x dot t. The y position we'll call x y t, and the y velocity we'll call x y dot t. And we got all those at time t minus 1. And we can therefore write that, and this little vector is then the state at time t, but we can write that let's do the velocity first for x. So the new velocity x dot t is equal to 1 times the old velocity x dot t minus 1 plus some noise, which we'll come to in a minute. So new velocity equals old velocity. And similarly, new position is old position plus delta times old velocity. So new position is old position plus t times, delta times velocity. And we do the same with y. Now, if you do the maths correctly and you integrate the Brownian motion on the velocity and think of it in terms of a stochastic differential equation, it tells you what the covariance matrix of the process noise, as we think of it, is, and that's shown in equation 7. Important point really is that we think of that as square root of the covariance matrix multiplied by some IID unit scale process noise V. So V is 0, 1 normal, or 4 of them technically stacked on top of one another. Okay, so and we also call this matrix here A. So the parameters of the dynamics are the A matrix and the Q matrix, which are often parameterized by delta, that we'll assume is the same for all time steps for at least ease of description. So we then talk about the likelihood. So imagine we've got NS sensors. So we've got them stacked together in this vector yt, and we've got the first sensor gives us a measurement of y hat 1 comma t. Second one gives us y hat 2 comma t down to y hat ns comma t, and then we get a some measurement noise on the top of that, and we describe that with a covariance matrix R, which is particularly problem dependent. E of t is then a 0, 1 stacked on top of another ns times normal distribution. And in this case, we're going to assume that we're measuring the range of my phone from various routers around the building, assuming they were working for once. And so y hat it is then just the square root of the square difference in x and the square difference in y positions between the phone x xt and the sensor sxi, so I sensor, and similarly for the y coordinate. So the I sensor is then located at sxi, syi. So here's our Stan file. This is what we want to produce. So we have a little data block in conventional kind of Stan type things. So we have the A matrix and the Q matrix, which will have been initialized sort of outside the stand file. With similarly the number of sensors and the sensors positions, the R matrix, the current measurements Y. I'll come back to that in a minute. And the previous state, which is a kind of placeholder that gets used by the by our particle filter. And we're interested in making inference about parameters that we'll call X. And we have a model down here which identifies some variables called the predicted measurement, predicted Y, dx and dy. And for each of the sensors, it works out what dx and dy are, and then predicts that the measurement, the y hat in the previous slide, is the square root of dx to the power 2 plus dy to the power 2, sticks those into a normal on the measurement y and into a multivariate normal on x, with mean of a times xt minus 1 and covariant q. So this, if all these things in the data block were known, would be a standard stand file. There's nothing new. We use it in a slightly different way, but there's nothing different about how the stand file is defined relative to a stand file that would just run normally. The only thing that you should hopefully know is that Stan would assume that X would be, I think it assumes between -2 and 2 uniform distribution, which pretty much is guaranteed to not be where you want it to be. So you would sensibly say, well, actually, let's say the process noise is between -2 and 2, and we're going to define X to be a transform parameter, which is basically the new state. And that would involve a square root of Q, which you would sensibly pre-calculate at the top. So that's the version of Stan syntax that we're aiming for in the alpha. Today, the version that works shifts the xt minus 1 to the parameter block, which is a bit annoying, and we're working to fix that, but that's the version that works when I'm giving this talk. Maybe when you're listening to this or when I'm answering questions, we'll have shifted it up again, but the version that works today has xt minus 1 in the parameter block. So what we do is this is the pseudocode for using the thing. We start off by saying we're going to make an engine. We're going to give it an incremental posterior stand file. We're going to tell it that x, xt minus 1 and y are xt minus 1 and yt, and we're going to give it some parameters. We're then going to initialize the PDF by essentially drawing samples from prior.stan. They actually will generate weighted samples, so that's not so important. And then the crucial bit is we have a while one loop that goes on forever, and every time it goes round, it gets the next data point, and then it does inference using the PDF that you had from the previous time step as the prior, or the recursive input, and Y as the input measurement, and it generates a PDF and perhaps some generated quantities, not shown above, terribly sorry, we'll do that later. And the PDF is then fed round in the next iteration of the while loop to the input. Crucially, this works. So not world's most exciting results perhaps show, but we have a particle filter that uses that Stan syntax and pseudocode, or actual code that looks a bit like that pseudocode, and generates the red dots as particles which track using range only measurements from the black squares to localize the object that's actually where the green small icon is. So we have a working almost alpha version of the syntax for pfStan. We're also doing a few things that you might find interesting. So we're compiling a little posterior DB for particle filters for testing. So comments and suggestions of particle filter problems you'd be interested in would be very welcome. We're integrating in a highly sophisticated proposal distribution so that we can tackle arbitrary problems well. We've also got a back end that works for SMC methods, include particle filters, so Cranch Monte Carlo methods. And finally, for our beta, which is slightly further ahead, but definitely coming, we're using Stan and PFStan to tackle the inference task that I described before, which will enable us to replace ODEs and Stan with SDEs and enable us to calculate likelihoods and gradients and use samples in Stan as well as PFStan. Thank you very much. Look forward to talking to you at the conference. Goodbye.